everybody. I am Sumiran Chattopadhyay. I have come here now today to talk about dynamic programming. It was a long demand from some of my subscribers that I create some lecture videos on analysis of algorithms, design analysis of algorithms. So I decided to start with dynamic programming. Why did I start with dynamic programming? This is because, as I understand, right now there are many interviews which are scheduled after a long slump. And in the interviews for technical rounds, dynamic programming is of immense importance. Be it TCS Ninja, be it Microsoft, be it Google, be it Amazon. Apart from your programming skills, they test your algorithmic skills, and in that, dynamic programming plays a very major role. Why it is so, we'll discuss. And we'll take two classic examples, very classic examples to demonstrate the working of a dynamic programming. In this lecture video, I'll rarely go to the coding part. I'll assume that given a recursive structure, the listeners can find out the codes themselves, write the codes themselves, or for many of you, those codes are not that relevant. You may just take the fun of dynamic programming and solving problems. We all know that recursion is a hugely used tool to solve programming problems, solve algorithms, find out algorithms to different problems. It is hugely powerful, but it has a number of limitations in terms of implementation. One such limitation would be that in recursion, the solutions that you have already done are forgotten. And sometimes those solutions are again required. So let us go to details of it and slowly see how we can move towards the beautiful realm of dynamic programming. We'll start with the very basic program which we have all done during our first year, the Fibonacci numbers. The Fibonacci series is all known to us. I mean, there are some variations, corrections. I'm not very sure about whether it starts with 0 or starts with 1, but that does not matter. Of course, it matters because the Fibonacci series is a famous series that it can only be unique. But then, for our understanding purpose, this series is good enough. Now, the problem would be given n, find out the nth Fibonacci number in the series. We can see easily that if I know the Fibonacci number n minus 1 and the Fibonacci number n minus 2, like Fibonacci number, I mean, if I want to have Fibonacci 3, like let's say I want to have Fibo. I want to have Fibo 3. So what do we do? I go to Fibo 2, which is 2, and Fibo 1, which is 1. I just sum them up and I get Fibo 3, which is 3. So if I want Fibo 5, I just go to Fibo 4 and Fibo 3 and I sum them up and I get Fibo 5. So the recursive formulation is very simple, very simple. And the recursive formulation is fib n is equal to fib n minus 1 plus fib n minus 2 if n is greater than 1, and if n is equal to 0, then fib n is 1. If n is equal to 1, then fib n is equal to 1. So there is a small correction here. The generalized formula is true for if n is greater than 1, and we assume that we start with the 0th number in the Fibonacci series. Now, having said that, let us see, a very simple code, therefore it is, those who are interested in coding, it's a first year code. So if I is less than 2, means it is 0 or 1, the result is 1. Otherwise, the result is call fib once again with I minus 1 and fib with I minus 2. The result of these two fibs are returned, and then that is added, and this result is obtained, and fib I is returned. So let us see a small working of this, of this algorithm or this program. So let us say I call fib5. If I invoke fib5, fib5 internally will invoke fib4 and fib2. Now we see fib4 to get completed must call fib3 and fib2. Now fib3 to be completed has to call fib2 and fib1. Now fib2 to get completed must call fib1 and fib0. Now why I do not have anything below fib1 or fib0? That is because fib1 does not call another function. It just returns 1, or fib0 just returns 1. So once fib1 returns and fib0 returns, then fib2 would be computed, and then fib2 will be returned. Now after fib1 returns and fib2 returns, fib3 will be returned. Similarly here, once this fib1 is completed and once this fib0 is completed, then this fib2 will be able to compute its own result and it will return. Now once fib4 is completed, this fib3 will be computed. But just have a breath now. You see fib3 has already been computed in this huge tree, and I am duplicating the effort here to do the same. So point is, I am doing much more computation just because I did not remember that fib3 returned me something. Not only that, just see this fib2 is actually here, here, and here 3 times. So if I have fib 11, fib 100, such duplications will be, exponential. And therefore, if I ask you a very simple question, let's say that how many times this plus will be invoked in case fib n is called, that also follows a very similar series such as Fibonacci. That can be proved, but that is not the point today. And Fibonacci number, is a hugely popular number, is a hugely used number, and has a lot of significance in nature. There are many natural phenomena which grows, shrinks in terms of Fibonacci numbers. So it's a very interesting number that stems out from mathematics, but has a lot of evidences to be present in natural and living world, plants, animals alike. So that's okay. So therefore, I find out that we are repeating a lot of computation that we have already done. In order to alleviate that, what I did is I created a one-dimensional array for every n. So for fib0, this will remember what is fib0. This for 1, this will remember what is fib1, and so on. Now, so what I'm doing, I'm storing the previous results in a table. The moment fib2 is calculated, the result is stored here. The moment fib2 is so to calculate fib3, I just need to consult these 2 entries in the table, and I calculate the number as 3. So no duplicated efforts. So we are reusing past computations from the table. This is very important. to understand. And therefore, I understand that if I do so, then I mean, you see, I'm growing it. I'm growing it. I mean, as if since I have the previous results, I use the past computations. This 5 and 8 will be added, and 13 will be there. Now 13 and 8 will be this 13 and 8 will be added, and 21 will be there, right? And so on. So basically, the lessons are two. We looked up previous results in the table reusing past computation, and if we do so, much less exponential time is required. Much less than exponential time will be required. And the big takeaway is therefore keep an array of subproblem solutions. Keep an array of subproblem solutions. In every dynamic programming problem, we'll find out that they're keeping an array of subproblem solutions so as that they can avoid recomputing every time the already obtained result. So this is a big hallmark of any dynamic programming. The other big hallmark of dynamic programming is, of course, I think we have written it. So dynamic programming, some of you who may be knowing about algorithms a lot more, is very similar to divide and conquer. After all, it solves problems by combining solutions to subproblems. These subproblems are not independent. So subproblems may share sub-subproblems, but solution to one subproblem may not affect the solutions to other subproblems on the same problem. Now they may. So this is a very interesting property. This is called optimality property of dynamic programming. I would not like to talk about the theory part of it right now. We'll talk about it definitely in another lecture video, maybe the next lecture video. But today we assume that if the sub-problems are shared in the sub-problems and they do not interfere with each other, then we can combine the sub-problems, the already obtained results of the sub-problems to get to the solution of the overall sub-problem, and then slowly I go to the solution of the entire problem. Now, if I look at it a bit more closely, then I can see that this entire array is not so meaningful. Why? Because when I am here, I'm just using these two numbers. When I'm here, I'm just using these two numbers. So what is the lesson now? Instead of keeping the entire array, we could have just two variables, previous and previous to previous. Summing them up, I could calculate the current number. And after calculation of the current number, the current becomes previous, and the previous becomes previous to previous. So naturally, I mean, in a traditional solution to a Fibonacci number, we do not see the dynamic programming nature of the solution because the solution does not use an explicit array. It does not need to. It can only use two variables to store the previous and previous to previous numbers and use them or sum them to calculate the current number. So that is why typically you will not see that a dynamic programming lecture video starts with a Fibonacci number problem. However, this solution has every hallmark that is required for any solution that is through dynamic programming. Next one is a little more interesting. Before that, just a few notes. So dynamic programming reduces computation by storing solution to a subproblem the first time it is solved and looking at the solution when the subproblem is encountered again. In fact, this way the subproblems are solved in a bottom-up fashion. So what is the key to this? Key to this is find out the recursive structure. Now, if you find out the recursive structure, you could go for a divide and conquer algorithm, or you could go for a dynamic programming algorithm. When you should go for a divide and conquer and when you should go for a dynamic programming is a question. That question will not be answered today. I will answer that in another video, the next lecture video. Today we'll look at the features of dynamic programming so that you can use it in your interviews, and maybe tomorrow I'll create another lecture video where you will find out more about dynamic programming. In fact, the number of classic problems involving dynamic programming is more than, I guess, more than 1,000, 2,000. So only 10, 15 of them are very, easy, close, and they are, or with their variants or their applications come in the interviews always. One of them is the next one that I will talk about, coin change problem. So assume that there is a vending machine which has an unlimited supply of coins of different denominations. Like for example, in Indian context, we can assume that there are 5 rupee note, there are 10 rupee, 10 rupee coins, 5 rupee coins. Sometimes there are 20 rupee coins. Maybe there are 2 rupee coins, there are 1 rupee coin. And the vending machine has an unlimited supply of that, and you probably can give a note, a paper note of rupees 100, and ask the machine to give out the change. Or you can give let's say a 50 rupee note and may ask for the change. Now the machine wants to give out as few coins as possible, as few coins as possible. Now why? Because it doesn't want to misuse its stock of the supply of coins. This is also faster. If 2 coins are to be dispensed, it will be easier and it will be faster. If 10 coins are to be dispensed, that will be more time consuming. Now, question is how to do this fewest number of coins. So, what we could do is we could look at one example. Look at one example. Let us say that I have coins of denominations 1, 2, 5, and 7. And somebody asked me to give a change of 4. Now, as a vending machine, I want to give minimum number of coins. So what will be my attempt? My attempt without any global knowledge would be to find out which maximum denomination I can give. In this case, 5 and 7 are rejected because they are more than 4. So 2 is the maximum denomination that I could give. So I gave 2, a coin of 2. So how much remaining? Another 2, 4 minus 2. So again, I need 2 rupees 2. And what is the maximum denomination that is with me for this coin? 2. So I give them 2 coins of 2 rupees each. And apparently this is the most optimal way. Now, if I want to I'll write it as an algorithm, then what we do is that, we give largest denomination coin which is less than it, which is less than it, and reduce n by the value of that coin and go back. Now, of course, what you could do, if you wanted to have, let's say, 27, and your rupees 27, you want to get a change, and your largest denomination is 7, then what you could do, you could say, I'm dividing 27 by 7 and get the quotient, which is probably 3, and could say that, okay, I'll give three coins of denomination 7, and then what remains is 27 minus 21, which is 6. So it is the same thing as kind of subtracting 7 again and again. So it may be the process will be a bit faster. Now, this slide I have already talked about to you. We told that, okay, this is a very nice idea, and maybe this gives me the fewest number of coins, the optimal number of coins. But the question remains, is it really optimal? Does this approach always give me the fewest number of coins? Is that right? Now, that is the question. Does this return the fewest number of coins? Now, the answer to that question is no. Now, when the answer is no, I need not prove it by mathematics. By existential theorem. I can just construct one counter example. Just one counter example will show that this result, the greedy result, is not going to work every time. And therefore, In general, this greedy approach or this algorithm that we just talked about may not be so functional. Now, why not? Assume that I have to change rupees 10 and my denominations are 1, 2, 5, 7. What is my logic? What is the largest denomination available to me? Since 10 is more than all of them, so I can choose either. The largest denomination is 7. So I give the customer a coin of denomination 7. What is remaining? Rupees 3. Now we cannot use coins of 5 and 7 to change rupees 3. So we have to give the customer a coin of denomination 2 because the largest coin less than 3 is 2. So let us give one more coin. How many is remaining? Just 1 rupee, and we give the customer a coin of denomination 1. How many coins therefore? How many coins? 7, 2, 1. Total 3 coins are given. Is this optimal? No. If easily I can see that I could have given the customer 2 coins of denomination 5. 2 coins of denomination 5, and that would be optimal. So the approach that we talked about is a very nice approach, but this approach will not help me in generating the most optimal solution, or in this particular instance will not give me the fewest number, minimum number of coins in exchange of the rupees that I wanted to change. So we have to think about a recursive solution if possible. Yes. So thinking about a recursive solution, what I need to know, given any n, what is this n? The rupee that I want to change. What is the minimum number of coins needed to give a change of rupees n? Now, if I say that give me a change of rupees 0, then naturally it will be 0. Now, if I ask you to give a change of rupee 1, how many coins are required? Only one coin is required because you have already a coin of denomination 1. If I ask you, I want a change of rupees 7, how many coins will you give me? Only 1, because there is a coin already available with denomination 7. So these 4 entries are known to me. Again, look at, like Fibonacci, I have created an array. Now, in this array, only 4 separate, not contiguous elements would be fulfilled at the very beginning. C1 is 1, because to change a rupee 1, only 1 coin will be required and of denomination 1. If you give me 2 rupees for a change, paper note, then I'll give you a coin of 2, only 1. If you give me a paper note of 5, I'll give you a coin of denomination 5. If you give me a paper note of 7, then I'll give you a denomination of 1 coin of denomination of 7. Now, question is therefore, if I want to find C3, meaning the minimum number of coins that I wish to give, if somebody wants a change of 3, right? So remember Cn. Cn is the minimum number of coins needed to give a change of n. So what is C9? C9 is the minimum number of coins required to give a change of 9, right? Minimum number of coins needed to give a change of 9. So can I find out C3? The question is, we need to understand how we can formulate it in a recursive manner. How can we use the solution to the subproblems to get the solution of the problem, which is C3 now. So let's look at it. Now, if I see what could be done, I can give the person a coin of denomination 1. So what is remaining now? 2. Now, do I know how many minimum number of coins I need to give for a change of 2? Yes, C2 tells me that. See, I have 4 coins. 1, 2, 5, 7. Now for 3, this is not possible. This is not possible. So I could use this one or this one. So let me try with this one. So I give the person a coin of denomination 1. So how much is remaining? 3 minus 1, which is 2. Now, for a change of 2, what is the minimum number of coins that I need to give? It's already there, 1. So my answer will be 1 plus C2, that is 1 plus 1, which is 2. You could definitely argue that what if I first decide to give a coin of denomination 2 to the person who wants a change of 3. That's right. We can ask that, and that will be discussed in the next slides. Like, for example, what about C4? Now, in C4, again, I have 1, 2, 5, and 7. This is rejected. This is rejected because they are more than 4. Now, I may decide to give a coin of denomination 1, and I have now, therefore, 3 rupees to give change for. Now, do I know C3? Yes, I know. So, what does it tell? It tells me that the answer is 1 plus C3, and which is 1 plus 2, not 1, 2, which is 3. Is it optimal? No, because we know that 4 rupees can be given a change with 2 rupees, no coin. So this is not optimal. So what went wrong? Yes. So one option is 1 plus C3. What if I gave her a coin of denomination 2? Then 4 minus 2 is 2 remains. What is C2? The answer is 1 plus C2. And 1 plus C2 is 1 plus 1, which is 2. So that is optimal. So I have to try with 1, I have to try with 2, right? I have, if needed, I may have to try with 5, I may have to try with 7. And even after doing that, if I see that my whichever is minimum, whichever gives me minimum among all of that I have to enter here. So I need to enter here 2, not 3. So C4 is minimum of 1 plus C4 minus 1, 1 plus C4 minus 2. Now what about C6? 6 is more than 1, 2, and 5, right? So to begin with, I could give a coin of denomination 1. So that is why 1 plus C6 minus 1. I could have given a denomination of 2. That is why 1 plus C6 minus 2. And I could also give a denomination of 5, and that is why 1 plus C6 minus 5. So this is 1 plus comes out minimum of C5, C4, and C1. Now C5 is 1 and 1, 2. C4 is 2 plus 1, 3, which is not the case, which we will not take. So this is actually C5 is 1, this is 2, and this is 1. So I may take this one or this one, but that will give me 1. So the result will be 1 plus 1, which is 2, and which is logical. I'll give him a coin of denomination 5 and a coin of denomination 1, right? So are you understanding the finding out the recursive structure, giving these examples? See, you will be given a new problem, not coin change problem, and you have to find out the recursive structure. So how do you find out the recursive structure? The problem that was given to you, you take it as an array, as Cn, as a cost of something, and then take examples and fill up this table. In order to fill up this table, find out how previous solutions are helping you out. It may not be as simple as just adding to previous numbers as was in Fibonacci, but it must be the case that previous solutions definitely help you very directly in getting the solution at hand. Right? Now, when I teach algorithm, I do not give you the steps of the algorithm. I tell you the examples. I tell you how to get to the solution, get to the approach. So now, if I ask you to tell me what is Cn, I am very sure that you can tell me what is Cn. For Cn, it will be minimum 1 plus Cn minus 1, 1 plus Cn. It will be C1 n minus 1, Cn minus 2, Cn minus 5, and Cn minus 7 in case n is greater than 7. right? So yes, that's right. And the moment you do that, you'll find out the C's like Cn minus 7, Cn minus 5, Cn minus 2, Cn minus 1 are all available in this particular array. And you want to find out a minimum of that. So how much time will it require? Maybe linear at the most. Not even linear. Then how many denominations do you have? 4. So it is order 4. If you have k denominations, it is order k. That's it. Right? But you have to grow it, no? If somebody asks you C9, you cannot assume that somebody gave you the table. So to get each one, you have to work for order k. And therefore the total complexity becomes order k into n. This k should be sufficiently smaller than the n. Therefore it is almost linear time. Right? It is almost linear time. But what is the cost? Because this problem is not that simple. But what is the cost? The cost is the space. The cost is the space. Look at the growth of this space. If I ask you C100, right? I mean, you have to have a space of 100, right? So there is always a cost to any gain that you actually achieve. I believe that I have kind of convinced you about how to find out the recursive structure, right? And therefore, I can simply generalize this. I have k dominations d1 to dk and n. These are the inputs. I want to write I1 into d1 plus I2 into d2 plus dot dot plus ik into dk such that becomes equal to n. And I want I1 plus I2 plus I3 plus ik. All these are minimized. So what is the solution? I just said find out Cn minus d1, Cn minus d2 to Cn minus dk, assuming that we are giving him first a coin of denomination d1 or d2 or dk. Get the minimum of that, of these c's. Just add 1 because you just gave him 1 coin, right? 1 plus that, and that is the solution for Cn. So I am getting a solution Cn with the solutions of the sub-problems, right? What a beautiful solution I got, right? And with that, you can fill up the entire array. Now, there are twists to this problem. Many twists to this problem. The minimum twist is this, without which I cannot conclude this lecture video. Is this okay? You said that if I give you 100 rupees note, you will give me 13 coins. Which coins, sir? Because if you do not tell me which coins, how do I know which coins? So therefore, which denominations did I use as a vending machine? So for that, I remember the last denomination used in dn. For example, so dn remembers the last denomination and pref links me with the column that was used to compute minimum. Just remember that here I am computing a minimum, right? And that minimum will be either d1 or d2 or d3 and so on, right? Not d1, n minus d1, n minus d2, n minus dk. So they refer to columns. They refer to columns, right? They refer to columns in the next table. So I'll give the example here very easily. So you see, C4 is 1 plus 4 minus 1, 4 minus 2, and 1 plus 1, 4 minus 2. So I put 2. So because 2 in the dn, I put 2 in the d4. Why? Because I use the denomination coin of denomination 2, one coin of denomination 2, and then I remember that how much is remaining. Amount of 2 is remaining. So where can I find that? I can find that out here. So if I go here, I will find out that one coin of denomination 2 was used to give the change. So this says to me that one coin. So this is the denomination. One coin of denomination 2 and the other coin of denomination 2. These are required to give a change of C4. Yeah, I can have some more. So for example, I have C7. How do I find out C7? Oh, C7 is easy because C7 is 1 from the very beginning. So let's say I want C6. So here 1 plus 6 minus 1, 6 minus 2 and 6 minus 5. Who wins? The 6 minus 1 wins. So what I remember here is I gave one coin of 1 root. I mean here this is the denomination of a single coin, and this tells me where can I get the remaining denominations. So I go to 5. So I come here, and here I see that again I give it one denomination, one coin of denomination 5. So how many coins did I give? I gave, let's say, 2 coins, one of denomination 1 and the other of denomination 5. Assume that I want to find out C, I mean the coins used in 9. So what is C9? What is C9? C9 is 1 plus C 9 minus 1, that is 8. C 9 minus 2, that is 7. C 9 minus 5, that is 9 minus 1, 8, 9 minus 2, 7, 9 minus 4, 5, that is 4. So what is minimum out of these three? C8 is 2, C7 is 1, and C4 is 2. So C7 is the winner. So which denominator should I use for 9? One coin of denomination 7. How much is remaining? 2. So now where should I go? To the column for. Here what do I see? Another coin of denomination 2 is to be given, and then nothing remains. Therefore, 2 coins, one of denomination 7, the other of denomination 2. So there is a link here which I have to traverse to tell you exactly which denominations were used to get to these 2 denominations. Now algorithms cannot be learned just by looking at a lecture video, listening to a lecture video, or by just reading a book. If you want to know algorithms, you actually have to work with examples. Be confident that the strategy that you worked out or somebody told you is something that you completely understood, you could completely grab it. Only then you can actually find out the true joy of learning algorithms. I told you at the very beginning that I will not give you the program. Sometimes I will not give you the algorithm even. In fact, I have given you the algorithm here. Only ground conditions are missing, which is CD1 is 1, CD2 is 2, CD1 is 1, CD2 is 1, CD3 is 1, CDK is 1. That is the initialization, and then this optimal substructures. And with that, I come to the end of this lecture video. I hope that you enjoyed it. Please leave your remarks in YouTube. I will definitely respond to your reviews, to your queries, if any. So have a good day. Thank you very much.